Hello and welcome. In this lecture, we will introduce the transfer function, which is actually a very compact representation of the ODE in the Laplace domain, and key features of the transfer function relevant to control analysis or relevant to dynamic systems. So the transfer function, let's consider the most general single input single output ODE. So you would have nth derivative of the output plus n minus 1th derivative of the output and keep going on, so on and so forth. First derivative of the output and the forcing function could have the mth derivative of the input m minus 1th derivative of the input and so on. First derivative okay. Arey yaar, this is aggravating. And in general, for realistic systems, n will be greater than or equal to m, and if you take Laplace transform of both sides for a system for which IC's initial conditions are 0, this is a key assumption, and initial conditions are 0 if the differential equation has been expressed in terms of deviation variables, deviation from the initial state of rest, initial steady state. So if you take the Laplace transform of both sides with 0 initial conditions, then what you will get is essentially y in the S domain, u in the S domain, in the Laplace domain, is equal to that's the numerator polynomial in S. You also get the denominator polynomial the denominator polynomial. This is called the transfer function g, which relates the output y to the input s, and the transfer function consists of a numerator polynomial and a denominator polynomial in s. You can factorize these polynomials, and in that case the transfer function, if both the numerator and the denominator have been factorized, would be To factorize, take bm common from the numerator and take an common from the denominator, and then you'll have the highest power of s as 1, and then you can factorize. And so what you'll get is bm by an times product over j going from 1 to m of the factors of the numerator, so s minus zj, and at the bottom you'll have product over I from 1 to n of the factors of the denominator, which I'll call p, denote by p. Okay, this is called a zero of the transfer function. These factors zj are called the zeros of the transfer function, and these factors pi are called poles of the transfer function. Notice that G is a very compact representation of the causal input-output system, where the input is U, output is S, output is Y, and the subscript S is dropped for convenience. So transfer function is a very compact representation of a dynamic system in the Laplace domain. The ODE in the time domain gets replaced by a transfer function in the Laplace domain. Okay, so the transfer function is a compact Laplace domain representation of the linear time invariant ODE with zero initial conditions. If you assume zero initial conditions, then this differential equation Laplace transforms to a numerator polynomial and a denominator polynomial. So this is the general form of the Laplace transform for a Laplace transform that relates an output to an input. Now if you factorize the numerator and the denominator, this is what we get. Numerator polynomial has been factorized, denominator polynomial has been factorized, and the numerator polynomial factors are called the zeros of the transfer function. The denominator polynomial factors are called the poles of the transfer function. And you have a very neat block diagram representation of the dynamic system. Now notice, if I was working in the time domain and I were to write the characteristic equation, notice that the characteristic equation would be an lambda to the power n plus an minus 1 lambda to the power n minus 1 plus a1 lambda plus a naught equal to 0. This is the characteristic equation in the time domain. Notice the polynomial over here. This polynomial is exactly the same as the characteristic equation polynomial, except that lambda has been replaced by s. So what we have is that the transfer function denominator polynomial is the same as the characteristic equation polynomial of the governing ODE, the ODE that relates an output to an input. Now if you have factorized the numerator and denominator polynomials, then you can see that the poles of the transfer function are the roots of the ODE characteristic equation. So what are the roots of the characteristic equation? they correspond to poles of the transfer function in the Laplace domain. So ODE characteristic equation roots in the time domain are equivalent to Laplace transfer function poles in the Laplace domain. Now let's think a little bit about the nature of the forced LTI ODE solution, forced by an input. Now see, the polynomial, both n and s actually, the polynomials that is equal to numerator polynomial divided by denominator polynomial in s. The coefficients of the powers of s in these polynomials are real. Because these coefficients are real, therefore the roots of these polynomials can be real distinct, maybe real repeated. What I mean real distinct is, for example, s minus a is a factor. You could have real repeated, for example, s minus b to the power 2. So that's s equal to b as the root repeated twice. You could also have complex conjugate roots, but they will have to occur in you could also have complex roots, but they will have to occur in conjugate pairs. Otherwise, you cannot get real coefficients of the powers of s. And you could also have, for example, s minus sigma minus j omega times s minus sigma plus j omega. These complex roots will always occur in conjugate pairs, always in pairs, always in conjugate pairs. So what we then have is, you could have total number of roots is going to be n total roots, total number of poles of the transfer function. Of these poles, let us say v of them are distinct, w of them are complex conjugate pairs, and q of them are repeated poles, with the kth repeated pole getting repeated r sub k times. I repeat, let us say the transfer function g has distinct complex conjugate and real repeated roots. The total number of roots has to be n, and let's just say, without loss of generality, that v of the poles are real and distinct, w of the poles or w complex conjugate pair poles are there for that transfer function, and you have then q repeated roots. So for example, s plus p to the power something, let's say, I don't know, well, to the power r1, s plus c to the power r2, and so on, s plus, I don't know, a b c d, I don't know, r q. So there are q roots. What are those q roots? B, C, and so on and so forth, D, that are repeated. So q roots are repeated, and the first repeated root, which is B, is repeated R1 times. The second repeated root, which is actually minus C, is repeated R2 times. Just to be consistent, let's keep the sign in the factor form. So the root B is repeated R1 times, the root C is repeated R2 times, and the final root, which is D, is repeated RQ times. So what we are basically saying is that there are a total of Q repeated real poles, and the kth repeated pole is repeated R sub k times. Okay. So distinct roots plus complex conjugate pairs plus repeated real roots, these must sum to n. That's just accounting for the number of roots. Now if you look at this expression, which if we use partial fractions, then we will have for each of the distinct roots, we'll have factors of this kind. For the complex conjugate pairs, we will have factor of this kind. The partial fraction will occur in this way: complex conjugate, complex pairs. Pairs implies they are conjugate. Oh, there must be a plus sign here. And then what we will have is, for example, if you have, let us say, one of the roots is s minus a whole cube. One of the factors is this in the denominator. So 1 over s minus a cube will factorize as, in partial fractions, it will be a over s minus a plus b over s minus a whole square plus c over s minus a whole cube. If it is repeated n times, you can keep extending this series. So for a root which is repeated rk times, for a root which is repeated rk times, the partial fraction would be sum over coefficient of the kth root and these coefficients, if there are 3 roots, there will be 3 coefficients. If there are rk roots, there will be rk coefficients. So I'll use L to index the coefficients, and then you will have s minus the particular root to the power L, L going from 1 to rk. This will be the partial fraction for one root, the kth repeated root, which is repeated rk times. And now you will have to have partial fractions of this kind for all the repeated roots, all the k repeated roots. So then you sum over k equal to 1 to q, because there are q repeated roots. So that is this term. And then of course you will have terms due to the forcing function. So g is this, and g is equal to ys by us, and therefore ys is equal to g times us. And when you start taking the partial fraction of this guy, you will get the partial fraction terms due to the transfer function itself, plus you will have terms due to the Laplace transform of u of s. For example, if u of s is a step, you will have g times 1 over s, that will be y sub s, and therefore you will get an additional term which would be for a step, which would be uh, a partial fraction coefficient divided by s. us could be a sinusoid or a cosine or a ramp and so on and so forth, but you see, you will get terms that are additional due to s, due to u of s, and these terms will have a form that is very similar to the forcing function itself. Okay, now if we now revert back to the time domain, then the time domain, this guy will go to summation ci e to the power pit. What will this guy go to? The complex conjugate pair, assuming that the Cj. Acha, by the way, I forgot to mention this, but complex conjugate pair, so the coefficients are also going to be complex conjugates. So this over bar indicates complex conjugate. So as I was saying, this goes to, in the time domain, summation ci e to the power pit. Let's look at this guy. What does this go to? This will go to Cj e to the power sigma j plus j omega j times t plus Cj over bar, complex conjugate, to the power multiplied by e to the power sigma j minus j times omega j t. And if I express Cj as in the polar form, the coefficient is expressed like this, and let's say then Cj bar is going to be same thing, except that the angle is now negative, and this assumes that the number c is in the first quadrant and or in the fourth quadrant. Anyway, so this is what this factorizes to, and therefore what you will get is this guy is actually equal to mod of c, the magnitude of Cj, times e to the power j omega t plus phi plus e to the power j omega t minus j times omega t plus phi, and there will also be e to the power sigma j t, and then you multiply and divide by 2, and therefore what you then get is 2 times mod of Cj, the coefficient, the partial fraction coefficient, times e to the power sigma j t times cos of, by the way, this is omega j t plus phi, and just to be consistent, because we are associating the phi with a complex conjugate pair, the jth pair, so we'll also have a j, an index here. Okay, so that's what this term solves to. And what would this term solve to? This term would be summation, the eigenfunctions are going to be ckl times t to the power L minus 1 times e to the power pkt, and this will be done for each of the repeated roots. So you take the sum over the each of the repeated roots, so sum over k and sum over L. That's what this guy will go to. And then of course you'll have terms due to us. For example, if us was a step forcing function, you would get a constant, a particular solution corresponding to which has the same form as u. Okay, so this is due to the distinct real roots. Okay, real distinct roots. This term is due to complex conjugate pairs. Poles that are complex conjugates, and these are real repeated roots, terms due to real repeated roots. And no matter what is the forcing function, these terms will always be there, and there will be additional terms that are similar to the forcing function itself. So if you correlate this with the method of constant coefficients, this will give you the particular solution, and and so on and so forth. Now let us look at the poles are giving us these transient terms. These are the transient terms. Transient terms means things that change with time. Transient means changing with time. Transient terms. So the poles are giving us transient terms, exponentials. These are called, of course, eigenfunctions. And you can see that if some characteristics, you can see that if pi is greater than 0 for a then the transient term is going to blow up in time. On the other hand, if pi is less than 0, then the transient term will decay to 0. Okay. Same thing applies to the sigma here. Sigma comes from the real part of the complex root. If this sigma is positive, of course there is the oscillatory part, the cosine part. Cosine part will always be between, or the sine part. The cosine or the sine part will always be between +1 and -1. It is the amplitude is actually going to blow up or diminish depending on whether sigma j is positive or negative. If it is positive, the e to the power sigma j is going to blow up, and therefore the oscillations are going to blow up if for sigma j greater than 0. If on the other hand sigma j is less than 0, then the oscillations will die out. That is sigma j less than 0. Same thing applies here. If pk is less than 0, you will get a decaying transient. If pk is greater than 0, you will get a transient that blows up. By the way, why does this not cause a blow up? That's because the exponential has this property. It blows up the fastest and it decays the fastest. So whatever is the increase because of the t term or t to the power something term, it's going to be overwhelmed by the decrease in e to the power pkt term. Okay. All right. So now if u is, what shall we say, bounded, obviously these terms will always be bounded. And so what that means is The stability of the system is determined by the fact, by the real part of the poles. If the pole has only a real part, you need to see whether it is on the negative real axis or on the positive real axis. Negative real axis means transients are going to decay, system will settle at a steady state. Yeah. On the other hand, if the real part of the if the real root is on the positive real axis, then the transient is going to blow up like this. Okay. Similarly, for complex conjugate pairs, if the real part is negative, the oscillations are going to die out. If the real part of the complex conjugate root pair or pole pair is positive, then oscillations are going to blow up. So what this means is that in summary, the poles determine the eigenfunctions of the transient response, the e to the power pt terms. The poles may be real, and the real roots or real poles may be distinct or repeated, or they may be complex conjugate pairs. I should add the word pairs here. The imaginary part in the complex conjugate pair results in oscillations, and you will see, our root was s is equal to sigma plus omega j omega. This was our root plus minus complex conjugate pair. Yeah. Now this, and you can see the cosine term. The frequency of oscillation is the same as the imaginary part, or the magnitude of the imaginary part, and the exponential envelope that determines whether the response is going to blow up or subside, the oscillations are going to blow up or subside, that is given by the real part. So imaginary part in complex conjugate pairs results in oscillations, and the frequency of oscillation is equal to imaginary part. Imaginary part, its magnitude of the root, imaginary part of the pole. If real part of a pole, whether complex or real, is negative, then the corresponding eigenfunction decays with time. If the real part of the pole is positive, then the corresponding eigenfunction blows up with time, and this gives this key result that if all poles of a transfer function are in the left half plane, then the system is stable. If any pole is in the right half plane, then that system is unstable, and we are talking of a single input single output system right now. So system stability, in general, the roots of the characteristic equation, and if you're talking Laplace domain, then the poles in the S domain, or lambdas, which are roots of the characteristic equation in the time domain. In general, these roots can be complex numbers. So let us look at the complex plane, the S plane or the lambda plane, as you will, and if you plot all the poles, some complex, some real, I don't know, maybe there's another one complex here, let's plot all the poles. If all the poles are in the left half plane, then the system is stable. On the other hand, if you get even a single pole in the right half plane, a single pole in the right half plane, you're going to get instability, because the transient because of that pole is going to blow up in time. So one must avoid right half plane poles when designing control systems. If there is an unstable system with no control, then we must design a controller that causes the poles of the closed loop characteristic equation or the closed loop transfer function to all be in the left half plane, so that the control system is at least stable. Yeah. Okay. So if any transfer function pole, which is also a characteristic equation root, is in the right half plane, then the system is unstable. Only if all transfer function poles are in the left half plane is the system stable. So this is like only if all of us follow social distancing and masking protocols will the spread of the virus get cut. If even a few of us do not follow these protocols, then the virus will spread. Or in India, as we say, एक मछली पूरे तालाब को गंदा कर देती है. One pole in the right half plane and the entire system is unstable. All right. Now let us look at the pole location and the corresponding transients. So if you have a real root or real pole in the right half plane, then you're going to get this exponential blow up. If you have a real pole in the left half plane, then you'll have this exponential decay. If you have a complex conjugate pair, that's the blue. If you have a complex conjugate pair in the left half plane, then you're going to get oscillations that die out, and the envelope of these oscillations is actually e to the power, oh dear, hang on, e to the power real part, and just to be clear, I'll say magnitude of the real part and put a negative sign there, times t. Okay. Hang on. And if you have complex conjugate pairs of roots exactly on the imaginary part, that means the real part is actually 0. Then e to the power 0t times sine or cosine of something, this guy is going to go to 1, and therefore you're going to get sustained oscillations that never die out in time. They also don't blow up. So you're on the verge of instability. If you have complex conjugate root pair in the right half plane, that's the red, these guys, the transient corresponding to this pair is going to be oscillations that blow up in time, and this is what we don't want. Okay. In all of these oscillatory responses, the frequency of the oscillation is the complex part of the pole or the characteristic equation root. Okay. So by looking at where the poles are located, you can start imagining what kind of a time domain transient response qualitatively you can expect. Now let us look at pole location and the transient response speed. So let's say I've got a stable system. Okay. Either it is open loop stable or I've put in a control system that has stabilized it. If I have a stable system, and let us say the stable system has a real root, and this root actually moves rightwards. And why will this root move? Because the system characteristics change over time, or because operating conditions have changed, or because you remember we saw those ordinary differential equations and tau was for those very simple systems was volume of the tank divided by flow rate, volumetric flow rate through the tank. Now if the volume of tank is constant, but if you are now flowing more, tau has changed. If tau has changed, the root is, tau s plus 1, so the root is actually corresponding to this capacity or capacitance is actually s equal to minus 1 by tau. So if f has decreased, tau has increased. If tau has increased, s would move rightwards. Yeah, so this movement in roots is very common because operating conditions or system characteristics change, or sometimes you may also change the controller tuning, and that can cause movement in the roots. Okay, so if this root moves rightwards, then you'll see that, okay, so I've got e to the power minus lambda t, that's the transient with some coefficient, and this will become, let us say, now you've gone rightwards, so lambda would have reduced. So if lambda reduces, the negative power actually reduces. Negative power reduces, that means the magnitude of this guy actually increases for a given t. So what you will get then are, if e to the power lambda t decays in time like this, if lambda has reduced, the decay will be slower. Yeah, so as lambda, which is the location of the root, decreases, that means my root moves towards the right half plane, the exponential decay becomes slower, the transient becomes slower, and this is what we have. And here the exponential has been, lambda has become 1/4 of the nominal lambda. Okay, all right. Now let's say I have a complex conjugate pair, and again these roots move rightwards, and let's assume for the time being that the real part remains the same. In that case, because the imaginary part remains the same, the real part, you move rightwards, you move towards the right half plane, so imaginary part is fixed. In that case, what will happen is the frequency of oscillation remains fixed, however the exponential envelope of those oscillations slow down, and therefore you will have the same oscillations, but the decay in the oscillations, because of the rightward movement of the complex conjugate pair, the decay would be poorer, things would decay slower. Okay, and that's what is shown here. Nominal response is the blue solid curve, and the transient response after the complex conjugate pair has moved rightwards is shown as the dotted curve, and you can see the exponential envelopes, the exponential envelope here and the exponential envelope here. The exponential envelope has slowed down, and therefore you get poorer decay, slower decay. The transient takes longer to decay. Okay, what if the real part remains the same, and so you have a complex conjugate pair, but now the imaginary part is increasing. In this case, the exponential envelope remains fixed, however the frequency of oscillation increases, and that's what is shown here. The frequency of oscillation has been doubled. Nominal is the solid line, and dotted is the moved apart conjugate pair pole. Yeah, so faster oscillations. So that is the impact of the location of the pole on the transient type and its speed. Okay, zeros in transient response. Zeros, let's see. You see, okay, these coefficients that we have calculated, these coefficients will change depending on the location of the zeros. The partial fraction coefficients will change depending on what's there on the numerator of the expression for y sub s. And it is because of this that the linear combination of the exponentials or the eigenfunctions, they change. And because you are combining them differently because of the zeros, the dynamic response will be different. So the zeros affect the dynamic response through the coefficients, the partial fraction coefficients. The zeros have no role to play in the determination of the eigenfunctions. The eigenfunctions or the oscillation modes or the transient modes, e to the power pt terms, these are determined exclusively by the poles. But the zeros affect the c's, the partial fraction coefficients, and through the partial fraction coefficients they affect the transient response. And just to make a slight point, let us say I've got a I don't know, a dynamic system whose I don't know, let's say a step response is, I don't know, like this. Okay, and now the system has been changed, and this is the step response for a system whose transfer function was g. Okay, and let's say u of s was okay. Now let us say that g has changed, and a 0 has been added, and to keep the gain the same, I'll have to divide by a. Yeah, I'll have to divide by a. So let's say the modified transfer function is this guy. G modified is this guy. Now if I force g prime, so this is the response for g. If I force the system with g prime with a step, so u of s is equal to 1 over s. Final value will remain the same as that of g. And why am I saying that? Because you can use the final value theorem. So y sub s is going to be 1 over s times s plus a times g over a, multiply by s and take the limit as s tends to 0. So this s and that s cancel out, s tends to 0, a and a cancel out, so you will have the same limit as s tends to 0, whatever you got by taking the limit of g. So you see the final value remains the same. So if the final value remains the same, that means I am going from here to here. But how does the presence of this extra 0 affect my response? So you can see that forget the 1 over a, this will be actually 1 by a times s times g plus a times g, or plus basically g. Yeah, so s times g is actually, this is the response when you're forcing it. Whatever is the response due to g, take the derivative of that, because s corresponds to derivative. And you can see what is the derivative here. Derivative is 0, then it will go up, and there's an inflection here, and then it goes down. So the derivative is actually, oh man, so let me change the ink color. So let's do this. So the derivative is actually, the derivative shape will look something like this. Well, that's not very well drawn. Maybe I'll draw it again. At the inflection, what you should be getting a maximum. So this is where you should be getting a maximum. So qualitatively, it will look something like this, and goes to 0. Sorry, forgive my drawing. And the sum of these two would then look like the sum of these two. So let me change the color again. The sum of these two would, after due scaling, you see that the response has become faster, and maybe you get a hump. Yeah. So a 0 will cause typically the response to become faster, and you may also start getting humps. Now, so you've got a 0. So let's denote a 0 with a circle, and let us say this 0 is moving right. If this 0 is moving right, the magnitude of A is becoming smaller and smaller and smaller, because this is A, and your 0 is at s equal to minus A. So if this 0 is moving rightwards, then if the 0 is moving rightwards, then you can see that s times g by A plus g. That's what you have. You're magnifying this more and more and more, because A is becoming smaller and smaller and smaller. So therefore, as the 0 is moving rightwards, this hump will become bigger and bigger and bigger. Yeah. An interesting thing happens if this 0 moves into the right half plane. Let's say the 0 is over here. Then what will happen? Then what will happen is, then your g prime is equal to, you're multiplying by s minus A, because A has moved to the right hand side, and therefore you'll be dividing by minus A and then multiplying by g, and this guy is going to be s times g over minus A plus g. So if you look at the response, you end up at the same final steady state. So you are ending up at the same final steady state. However, initially you are going the opposite way, because now it's this negative sign. The g is moving it one way, the derivative with that negative A is moving the response the other way. So now the hump will add in a negative sense, and therefore you will get something that looks probably like this. Yeah. So when you have a right half plane 0, you start getting these inverse responses. Yeah. This is called the right half plane 0, and this is called the inverse response. So zeros affect the partial fraction coefficients, and because of this change in partial fraction coefficients, the dynamic response gets affected through these coefficients. Right half plane 0 causes an inverse response, left half plane zeros accelerate the response, may also cause a hump. Zeros have no role in determining the eigenfunctions or the transient modes, the e to the power pt terms. They are determined exclusively by the poles or the characteristic equation roots. Now, if a dynamic system is given to us, the first thing we should do is factorize the numerator denominator, get the poles and the zeros, and plot them on the s plane or on the lambda plane. So here I'm just showing you something, so it's got 4 poles that are denoted by these crosses, 1 2 3 4, and it's got a 0 that's denoted by that big dot. What does this indicate? We see that all poles are in the left half plane, and therefore the system is stable. That's the first thing that we can tell. Now, for a stable system, the pole closest to the right half plane has the slowest transient. You see, this guy will be e to the power minus, let's say, lambda 1t. This guy will be e to the power minus lambda 2t. This guy will be some constant times e to the power minus lambda 3t times sine or cosine of something. Yeah, these are the transient terms that you're going to be getting, and you can see that because lambda 3 in terms of magnitude is the smallest, if I look at these, if I plot the e to the power lambda t terms, e to the power minus lambda t, lambda 1 magnitude is the largest, so it will decay the quickest. E to the power minus lambda 2, it will decay but not as fast. On the other hand, this guy, because its lambda 3 magnitude is much smaller, the decay would be, I don't know, I'm just much slower. Yeah, so lambda 1 corresponding to lambda 2 corresponding to lambda 3, what are we plotting? E to the power minus lambda t. Okay, so you can see that these transients die out quickly, so the overall response is governed or is approximately dictated by those poles that are closest to the right half plane. So that's what is stated here. For a stable system, the pole closest to the right half plane has the slowest transient, and in terms of closeness, this is a complex conjugate pair, these are the closest. Okay, therefore it dominates the transient response. Okay, now imagine a situation if the other poles are sufficiently away from the dominant pole, then the transient response is approximately the same as the response due to the dominant poles, and this is referred to as the dominant pole approximation. So even from the point of view of stability, when you're tuning a controller, because the characteristic equation or the denominator of a transfer function will be a function of the tuning parameters, as the tuning parameter is changed, the coefficients of the denominator polynomial change, and therefore the roots change. So the roots or the poles move as the controller tuning is changed, and typically what will happen is some of the roots will move leftward, some of the other roots or poles will move rightward. Now the ones that are moving rightward are going towards instability. These ones, the one that approaches the right half plane first, the one that gets to the right half plane the quickest, that's the one that is the dominant pole, because the transients because of that will be the slowest while it is in the left half plane. And if we prevent this particular route or pole which goes rightwards as tuning is made more aggressive, for example as the controller gain is increased, these guys will move rightward. This is what typically happens. Okay, so the whole idea in controller tuning is to make sure that these critical routes that tend to go to the right half plane the quickest, these remain sufficiently away from the right half plane. So in a feedback control loop, some of the closed loop poles move towards right half plane as Kc is increased, and so the key control idea is tune the controller such that the dominant closed loop pole. What do you mean by the dominant closed loop pole? the pole of the closed loop system that is closest to the right half plane, such that the poles that are closest to the right half plane are sufficiently away from the right half plane. And how is this done in practice? This is done by typically the pole that is closest to the right half plane. This will typically occur as a complex conjugate pair. It will not be a real pair. Most often it is usually a complex conjugate pair. So for that complex conjugate pair, what you typically then say is that the damping coefficient, this is not correct, should be between 0.3 and 0.5. Please make a correction here. Should be between 0.3 and 0.5. Okay, how is this, how does this relate to the pole 0 map? What we are trying to say is, remember phi, the angle phi is equal to cos inverse, and by ensuring that cos phi is between 0.3 and 0.5, we are basically making sure that the imaginary part is not too large. So in control systems you will also see, and we will see this in much more detail when we do root locus. I had indicated it earlier. Initially this is greater than 1 at low Kc. Then as is much greater than 1. Then as Kc is increased, it approaches 1. Then it becomes equal to 1. Then it starts going less than 1. And if you keep cranking up Kc, you'll get sustained oscillations. And if you crank up Kc further, you'll get instability. So the roots, so initially the response is slow and sluggish, then it gets faster, but it is still exponential, and then you start getting oscillations. Then you start getting faster oscillations. Faster oscillations means the roots are moving outwards. The roots are complex conjugate roots are moving outwards. Outwards meaning their imaginary parts are increasing. So the oscillations become faster, then you get sustained oscillations, and then you start getting oscillations that are still faster and that blow up. So basically the direction of motion of these roots is typically of this kind as Kc is increasing. So then what you say is that the root that is closest to the right half plane, which in this case are these two roots, if there were two other roots of this kind, we would still focus on this guy because these are closest to the right half plane and therefore they dominate the transient response. The transients because of these guys are going to die out very quickly. Yeah. So what we are now saying is that by ensuring that the damping coefficient of these two dominant roots is sufficiently away from 0, that means sufficiently away from the right half plane, because when the damping coefficient is 0, then you get these roots exactly on the imaginary axis. So by ensuring the damping coefficient is between 0.3 and 0.5, you ensure an oscillatory response. Oscillations imply that the response is fast, but it is not too oscillatory, and that's the kind of thing that gets done for tuning control systems or control loops or PID controllers. So in summary, the transfer function implicitly assumes 0 initial conditions in the governing ODE, and it is a compact representation of the ODE in the Laplace domain. The numerator polynomial of the transfer function and the denominator polynomial of the transfer function constitute the complete transfer function. The roots of the numerator polynomial are the zeros of the transfer function, and the roots of the denominator polynomial are called the poles of the transfer function. The transfer function zeros affect the transient response by affecting the partial fraction coefficients. The transfer function poles, much more important, these are the roots of the ODE characteristic equation. In fact, the denominator polynomial is the same as the characteristic equation polynomial. The roots or the poles of a transfer function may be real, may be complex conjugate pairs. When real, the roots may be distinct or repeated. The roots occur in complex conjugate pairs because the coefficients of the numerator or denominator polynomials are real numbers, and therefore they must occur in complex conjugate pairs. These poles determine the eigenfunctions, the e to the power pt terms in the transient response. The transient response is a linear combination of the eigenfunctions, and what linear combination is governed by what occurs in the numerator, and hence the zeros affect the transient response through the particular linear combination of the eigenfunctions. The complex conjugate roots cause sinusoidal oscillations, and the frequency of these oscillations is equal to the imaginary part of the complex root. The system is stable if all the poles are in the left half plane. If even one of the roots is in the right half plane, the system is going to be unstable. The dominant pole in a stable system is the pole closest to the right half plane, and it is called the dominant pole because it dominates the transient response. And the key control idea is that in a feedback controller, one should do a tuning such that the dominant closed loop pole remains sufficiently away from the right half plane. So you get a stable, desirable closed loop response. With this, we come to the end of this lecture. This was more of a conceptual lecture. No numerics or anything of that sort in this lecture. Thank you for your kind attention. Hope to see you again. Thank you and goodbye.